All right, we are in lesson 16. This is video F. We're going to continue and look at some examples. Joe talked last video about type 1 and type 2 errors. So let's look at a couple. Recall we looked at this college cheating example a few lessons ago where we looked to test is the proportion of students that cheat, is it 0.75, 75% versus is it more than that? We wanted to determine if more than 75% of college students cheat. So we obtained in that test a p-value of 0.0015. Based on that, we rejected the null hypothesis in favor of our alternative. So the question with this one is, in doing that, in rejecting the null hypothesis in favor of the alternative, what kind of error could we have made? And what are the chances that we did? Okay, so what kind of error could we make? There's type 1 or type 2. Since we rejected the null hypothesis, the type of error that we might have made would be a type 1 error. That happens when you reject the null hypothesis, but it's actually true. So let me get a clean piece of paper here, and we'll say first of all which one we made. So since we rejected the null hypothesis, it's possible that we made a type 1 error. And then the second part of this is to talk about what are the chances that we did this. So that answers the first part. What are the chances that we did this? Look back at the top there. You have a p-value. Your p-value is 0.0015. So this is the likelihood of making a type 1 error. And I guess before I write that, a type 1 error in the context of this problem would be that we concluded that more than 75% of students cheat when it was actually 75% or below. So just to even write out in the context of the problem what this is. We concluded more than 75% of students cheat. But a type 1 error would be making that conclusion when in fact the percentage was 75% or less. And then the likelihood of that happening, that's where the p-value comes into play. So that p-value, again, was 0.0015. If we think of that as a percentage, multiply that by 100, there's a 0.15% chance that we concluded more than 75% of students cheat when it was really 75% or maybe even something less. So the likelihood of this happening is pretty darn small here. And I'll express this as a percentage. So there's a 0.15% or a 0.0015 probability that we made this error. That's pretty small. Like, keep in mind that number. This is 1.5 out of 1,000. So could have happened, but not very likely that we made that type of error. All right, let's go to the second one. Erase this. The second one problem refers back to a problem we looked at earlier as well about attendance at a school. So we looked at a problem where we looked at high school attendance, and in that problem, the null hypothesis was that perfect attendance was 34% or 0.34 versus that it had declined, that it was less than 34%. We were trying to determine if perfect attendance rates had declined below 34%. In that test, we got our test statistic, we got our p-value. Our p-value was 0.0901, and based on that, we failed to reject the null hypothesis. We kept this. And so with this one, what kind of error could we have made? When you fail to reject the null hypothesis, but the alternative is true, that's a type 2 error. So I'll write that down in a second. And then we'll write down what that means in the context of this problem. So let me get a clean slide here. So since we failed to reject the null hypothesis, we could have made a type 2 error. Okay, so what does that mean? A type 2 error means that, let's see, we failed to reject the null hypothesis. We said we didn't really find any evidence for a decline in perfect attendance, when in reality, perfect attendance had declined. All right, so again, a type 2 error in the context of this problem. We did not find evidence that perfect attendance had declined when it actually had. So if that's the case, then we would have committed a type 2 error. All right, let's look at one more. This, I think, is a new problem we haven't seen yet. So we have an allergist in Indianapolis speculated that perhaps the reason why allergies and asthma have been on the rise over the past 100 years or so is because people are no longer exposed to farms like they were in the past. He hypothesizes that exposure to farms, particularly cows, influence the bacteria in our guts and sort of stimulates the immune system. Today, 1 in 5 Americans are allergic to food or pollen. 1 in 5, if you take 1 out of 5, that would give us 0.20 or 20%. So just a comment, we're going to use that here in a second. Oh, okay, hold on, there's more to this. Let me go to the next slide with the rest of the description here. The allergist noted that Amish come from German-speaking people of Switzerland, where the percentage of people with allergies is the same as that of in the United States. So he doubted that the difference could be due to genetics, so sort of ruled that out. To test his hypothesis, he looked to the Amish community in northern Indiana, where 92% of children work either on a farm or exposed regularly to farms. He looked at a sample of 138 children, and 10 of them had allergies. Okay, so now we're ready to test his hypotheses here. So test the hypothesis that the proportion of Amish people from northern Indiana is less than that for all Americans. And remember, if I go back real quick, all Americans were saying about 20% of Americans have food allergies. And we want to test here to see if the proportion of Amish people from northern Indiana, if that proportion is less for them. So first thing, let's write up our hypotheses here. You either have allergies or you don't. This is a categorical variable. We're interested in the percentage of people with allergies. So we're going to assume that it's 20% like it is today for all Americans. And we want to test to see, is it less for the Amish people in northern Indiana? So less than. If I just mention the conditions, talked about 1, we definitely have a categorical variable. You either have allergies or you don't. Our sample, we'll assume that this is an unbiased sample of kids. Our sample size was 138. Again, it seems reasonable that 138 is less than 10% of all the children in this community. So we'll assume it's less than 10% of children in this community. And then finally, your success-failure condition. We need to have at least 10 successes and 10 failures. And right above Part A, it tells you there are 138 kids altogether. 10 had allergies, and so the other 128 didn't. So we have 10 with allergies and 128 without. Both of those are at least 10. We've hit 10 here with this one. So our conditions for hypothesis testing hold. Since this is a proportion problem, the next thing you do is compute your z-test statistic. To do that, we need a few things. We know what our hypothesized value of p is. We know what our sample size is. From the data, we need to figure out what was the percentage in the sample that had allergies. So from the sample, there were 10 kids that had allergies out of the total. If you take 10 out of 138, let's see. In the sample, it was just over 7% had allergies. You get 0.072, so about 7.2% in the sample had allergies. And now you're ready to compute your test statistic. We've done lots of examples with hypothesis testing for proportions, so you should pause the video right here. Hit pause, make sure you can get that. Make sure you can get the p-value. You're going to take p hat minus the hypothesized proportion, divide by the square root of p times 1 minus p divided by your sample size. And so you should make sure you can do that, verify that. Your test statistic should turn out to be negative 3.76. And so even based on that, you should kind of have a rough idea what our conclusion is going to be here already. If you draw out the normal curve, plot your test statistic of negative 3.76, shade the tail to the left, you should be able to compute the p-value. So verify that you can get this too. And your p-value, 1, 2, 3, 4 zeros, 8, 5, is very, very small. And remember, the smaller the p-value, the more overwhelming evidence we have in favor of the alternative hypothesis. So this is extremely small. This is a very strong reject the null hypothesis here. And we might even say, given that that p-value is so small here, that we have overwhelming evidence in favor of the alternative. And last thing in A, maybe I'll try to squeeze it up at the top. In addition to making your decision, we go ahead and we say what that means in the context of the problem. If we reject the null hypothesis, we found, in this case, overwhelming evidence for the alternative hypothesis. We did find evidence that that the proportion of Amish people in northern Indiana, that the proportion that have allergies is clearly less than it is for all Americans. So, let's see if I can fit this here. We conclude this population, I'll abbreviate that, of Amish children has fewer allergies than the general U.S. Population. So that would be our conclusion. All right, we're going to have a couple more parts to this one. We want to look into that p-value and talk about if we did make an error, is it possible that we made a type 1 or a type 2 error? So I'll flip the slide. Again, pause if you need to. Make sure you can get those values. You should be able to by now. All right, we're going to interpret the p-value with a sentence here. So let me erase some of this. Erase my sample proportion, that's okay. Let me just talk about this and then I'll write down the answer. That p-value, what that is, in your sample, p-hat was 0.072. That p-value, what that is, if the null hypothesis is true, if 20% of these Amish kids really have, or in general, if the population in general has 20% of us have allergies, how likely are you to get a group where in a sample, only 7.2% of them have allergies? Could that happen? And you know, it could happen, but how likely is it to happen? How likely is it to happen? Here's the likelihood. So, and that's the p-value. In this case, not very likely at all. So in this community, if the likelihood of having allergies really is 20%, you would get a sample where 7.2% or say even less had allergies, with a probability that's exceptionally small. So let's write that in a sentence. So if this Amish community really has 20% of them have allergies, first sentence, that's assuming the null hypothesis is true. We get a sample. Like we did. Or one even more extreme. So you could even say, or fewer. And if I convert that p-value to a percentage, I'll move the decimal over 2 places. I'll now just have 2 zeros instead of the 4. This would happen .0085% of the time. So extremely rare. Not just rare, this is, extremely rare. And because that's so rare, we conclude that the percentage in the community that suffers from allergies must be less than 20%. That was our conclusion, because could this happen? It could, but the likelihood of that happening was not 0, but man, was that extremely small. Okay, so that's the interpretation of the p-value. The p-value is always, if you assume that null hypothesis is true, how likely would it be that you get sample data like you did, or even more extreme. The last part with this example is, if we happen to make an error in this one, it's not very likely, but if we happen to have made an error with our conclusion here, what type of error would it be? In this problem, we rejected the null hypothesis. So when you reject the null hypothesis, there is a chance that you make a type 1 error. So what type of error might we have made? It's possible we made a type 1 error. And you might even pause the video again here and try to write out for yourself, what's a type 1 error mean? A type 1 error is when you reject the null hypothesis, but it was actually true. So can you write that in the context of this problem? What does that mean? Not only what does it mean, how likely is it to happen, the p-value is the probability of making a type 1 error. So we just saw what that was. It was extremely small. There's a 0.0085% chance that we concluded that less than 20% of people in the community had allergies, when in fact the percentage was 20%. So we can actually even pull the probability of this back into it. Here's a 0.0085% chance. That we made a mistake by concluding that the community has less allergies when in fact they're just like the rest of the country at 20%. We conclude this community has fewer allergies when in fact so there's always a chance that that happens, not very likely in this one. We feel pretty confident in our conclusion with this one, given how tiny that p-value is, how small the likelihood is of making a type 1 error. All right, at the bottom of the page, we just have a couple things, notes to make about type 1 and type 2 errors, and then that will wrap this video up. So, some more things about the probabilities of type 1 and type 2 errors. In MAT127, we're going to give you sort of 3 nuggets of information that pertain to the managing the probability of making errors. If you take our Stat 2 course, they would cover these ideas in more detail. The first one, these are mistakes. So the only way to reduce at the same time the likelihood of making a type 1 error or a type 2 error is to increase our sample size. If you collect more data, then you'll have more faith in your decisions and you'll be less likely to make an error. So the only way to simultaneously reduce type 1 and type 2 errors is to collect more data or increase your sample size. All right, so that's the first thing. Second bullet. Sometimes the consequences of making a type 1 error are more severe than the consequences of a type 2 error, or the other way around. It turns out that you'd think we'd like both of these probabilities to be really small. The problem is those probabilities move in opposite directions. So if you increase, as the probability of a type 1 error increases, the probability of a type 2 error decreases. So we can't just say we'd like both of these to be extremely small. As you make one small, that inflates the other one. The opposite of this is true as well. And then finally, if you decide to reject the null hypothesis, blank is the probability that you're making a type 1 error. That's what the p-value is. you reject the null hypothesis, the p-value is the likelihood that you make a type 1 error. And therefore, the what you make the p-value, the less likely you are to make a mistake. Obviously, the smaller that p-value is, then the less likely you are to make a type 1 error. So the smaller that is, the more unusual or the more unlikely it is that you have made a type 1 error. Okay, that wraps up this video. Thanks for watching.